Hi. So this first question, I think, is for both Min and Ashmitha. So the questions is about. So you talked a ton about performance improvement initiatives across the stack that was done for Llama 4 and beyond. So how do you identify what bottlenecks are in workloads and in like collectives, and how do you stack rank these like performance initiatives, and what do you kind of decide to work on first and things like that?
Yeah. You want to go first?
Ashmitha, you want?
I can go first.
Yeah, go ahead.
Yeah, so usually we do a top-down and a bottom-up combined observability over here. From top-down, we work with model developers to look at the candidate choice and look into the aspects about, for example, which communication are exposed and which communication are overlapped with computation and how they skew of collective across ranks ongoing. After we identify there is a communication-specific issue, then we hand over this to Ashmitha to do a bottom-up observation. Yeah, you go.
Yeah, so I would say on top of profiling, like we also look at like metrics, different. So on the network fabric side, we have metrics like PFC, ECNs, and buffer utilization, port utilizations, which pretty much tell us like there is like congestion or congestion happening in the network. So these are pretty good indicators, and this can like these metrics directly tell us like there's an impact on the collective performance. So I can give an example like the all-to-all example, which I just shared. So when we first enabled zero-copy all-to-all, like the performance wasn't great when we integrated with the workloads. So we saw that the all-to-all performance was much lower than what we benchmarked. And so later, like looking at the traces, we saw that the collective kernels were taking longer because we were seeing a lot of RX pauses on these NICs. So yeah, just by looking at network metrics and host side metrics, like we can get a lot more information about where the bottlenecks are. Yeah.
Awesome. So yeah, so essentially both the model side metrics, top down, but also like the bottoms up or more distributed metrics from the NIC and the network, together give you an idea of what to work on or what performance initiatives to take up. The next question is for Saif. So Saif, the question is, can you compare and contrast like optimizations for the initialization scaling, the model initialization scaling that you talked about, as well as like fault tolerant training? Essentially, are both of these necessary for optimizing the effective training time, or are these like complementary? Is there like a choice between one versus the other?
I see. Yeah. So yeah, that's an interesting question, because I think as you have large number of resources participating in a job, right? Your initialization problem is bounded by that. So in fault tolerant, that's not a problem because your replica size is effectively 4K. Versus your replica size effectively is 100K in the other problem. So you don't have to solve like initialization problem for the fault tolerant training. So in that way, they are both like a parallel strategy to achieve an effective overall throughput training time. Yeah.
Awesome. Yeah, that makes sense. So the next question is for Ashmitha specifically. So you talked about this TQPLB, a software-based load balancing scheme, but you also have hardware-based load balancing schemes. One was talked about earlier in the day, like DSF, that does cell-based spraying, and then we also talked about enhanced ECMP in the past networking at scale. So how do you compare and contrast like software-based load balancing schemes and their effectiveness and hardware-based load balancing schemes and their effectiveness?
Yeah, that's a good question. So definitely hardware-based load balancing schemes are much more superior or sophisticated, I would say. So, but these solutions are pretty new. Like we do not have this deployed in a lot of our clusters, and so majority of our fleet still uses ECMP or the enhanced ECMP mechanism, where the flows are basically using like a 5-tuple identifier and like the source destination queue pair information and hashes them on different links. So with ECMP, we definitely get better through entropy, but it still is not like a perfect solution when it comes to load balancing. So there are still few cases where we get uneven traffic distribution. So having this kind of software-based load balancing definitely is like an added advantage on top of ECMP. So
that makes sense. That makes sense. So the next question is for Min. So Min, you talked about Nicklex communication library and a custom software transport CTRAN. So how does Meta consider build your own versus like use existing open source libraries, communication libraries like Nickel? I'm guessing this is talking about like a NVIDIA Nickel baseline, MPI variants, MSICL++, and a bunch of, there's a long list here.
Well, that's a very good question. So, frankly speaking, we actually did a long time to study by ourselves to debate about whether we want to invest in our own custom transport or we leverage the existing vendor implementations. So we studied that even from Llama 2 time. So in the past couple of years, we identified there are some pros and cons, but we see the benefit more than cons to make our own custom transport. Specifically, thinking as NVIDIA Nickel is more like a GPU collective point, very specialized library. We see more and more requirement for communication needed to support our training. The very specialized library is no longer sufficient to support that very quickly. On the other side, like MPI, which actually I was an MPI developer, so I loved MPI. It's a very generalized library. It gives whatever communication semantics and allow you to write actual communication algorithms, but it's too generalized, it's too fat. So we want to actually get something in the middle. It specifically allows all the algorithms needed for our language model training be random, but not everything. So that's why we spend a lot of time to build our own custom paths, and we get a good part from both the vendor specialized library for highly performance critical paths, and also we get the generalized communication semantics experiences from the very generalized MPI side.
Yep, makes sense. So it's all about finding a middle ground, right? Yeah. So this next question is for Saif. So Saif, you talked about fault-tolerant training, reducing the interruptions from like 100K scale to a single replica size, like you said, I think 4K or 8K GPUs. So how do you reduce the interruptions to even smaller size? Like how can you reduce that replica even smaller?
Yeah. So I think that's like it depends like a lot on the model size. So if you have very large model, your replica has to be somewhat like, which can fit the model. That's one of the parameter to go after. The other parameter is that like you can use various other techniques, like because as you shrink your like a GPU resources to fit a model, the key thing that gets pressed is the GPU memory. Right. So while the compute, it will be just slower, but the memory, if it cannot fit, it will just blow up and your job wouldn't train. So you just need to then use various techniques that exist, like offloading the parts of the model during like when they are not needed to push them to CPU, because GPU has 80 gig, 90, 100 gig memory for H100, for example. But CPU has 2 terabytes memory. So it's slower bit. But if you don't need, you can push stuff to CPU and then like pull. But it's a trade-off again, right? So you can't just use CPU memory like a GPU memory. And it may slow down if you don't do it carefully enough, it may overall slow down that aspect. Another key aspect maybe is to like that if you have a very large resource, the failure probability could be in one of the replica. Now, if your replica size is too small, you may have 2 replicas down at the same time. So that's one of the dimension like which can be explored based on some statistical analysis from the number of resources involved, as well as like the performance requirements that we want to extract out of from the model training. Yeah.
So staying with you, Saif, like another question is around fault-tolerant training again. Essentially, fault-tolerant training seems a magical new paradigm for improving efficiency. So what are the challenges with it? Like, why is it not widely in use everywhere?
Correct. Yeah, so I dodged that bit in my talk because we didn't have enough time to cover like a lot of pieces in there. But that's definitely like again, I mentioned and emphasized that it's a new paradigm, right? So it's not something widely adopted in an industry. The key difference to note between 2 training models like which is like one with the single job model, one with like a fault tolerant model. When you have your checkpoints produced, right, and if you have a failure, you go back to your checkpoint and resume from there. And the results you get at every steps are identical if you go back and resume. But on a fault side, as you would have noticed, it would be a different behavior because for your faults are randomized, first of all. And second, for the duration of the time you have your replica down, you're only training with n-1 replica. So in that case, your model is outputting slightly different behavior at that point in time. So your reproducibility is lost there. But it is on a thesis that eventually even though there is no reproducibility may not be there exactly, but it's aiming towards the convergence at the end. And it will perform on a similar way that if you train with like a single resource job. So you train faster, but with a slight risk of your numerics effectively. So it's more about getting like a lot of experiments getting done and figuring out the right balance here. And,
I see. So it's magical, but magical with trade-offs. Yeah, right.
Comes with, yeah.
So then this next question is for Ashmitha. So Ashmitha, you talked about assigning different parallelisms to different stages of the network. And then I think per network layer tuning of outstanding data, and then per collective or specific collective tuning for all-to-all. So how does Method keep track of like all of these configurations for these tunable parameters? And do these like configurations apply generally for all kinds of workloads, right? Inference, post-training, pre-training, and so on?
Yeah, I must say, like right now, a lot of this configurations are like manually tuned and handcrafted. So it's a bit of a pain at this point. So we do like maintain different set of configs for different workloads and optimize them accordingly. So yeah, there's like a lot of hand-holding. Before we start model training, we have to figure out these parameters. So yeah, but at least in the future, our goal is to have some kind of framework that can auto-tune them. And yeah, we are working towards that right now. But
makes sense. Yeah, auto-tuning is the future. So this question is for Min. So this is addressing a very specific like NVIDIA Nickel capability. So the question reads like, doesn't Nickel already have zero copy or user buffer registration support? This is specifically referring to NVIDIA Nickel, I think. Can you elaborate your claims about Nickel baseline limitations?
Oh my, okay. Very detailed question. Yeah, we can go in deep here. So first of all, we started the zero copy implementation at the Llama 2 time. At that time, Nickel didn't have zero copy. We told them we need that. So the sequence is different, okay? So later, let's just go what we have now in both our custom stack and NVIDIA Nickel. We both have buffer registration. It uses actually the same user buffer registration API, Nickel Con register, Nickel Con deregister. But just the upper layer, which is PyTorch layer behavior, and the under layer, which is within the COM register behavior is slightly different in the NVIDIA library and the custom path. So specifically, NVIDIA Nickel library gives user the full control on user has to manually, explicitly register every buffer that has to be used for collective zero copy. So user make the basically control on which buffer needs to be registered and or not. Every time you call con register, that's an actual network registration. It's expensive, milliseconds, sometimes tens of milliseconds. On our side, we first chose to give a transparent buffer registration by integrating with PyTorch cache allocator. So in con register function call, we don't really register every single buffer to network, but just cache it. Whenever the buffer is starting used in a collective, we register that first time it's getting used. It works very good, actually, and it doesn't require any user code change for zero copy being enabled. But I would say in some special cases, as we also discussed during the talk, there is a low reuse case that we will see in some model parallel domains, such as pipeline parallelism. So we need to use a similar mempool kind of approach, which has already been integrated in PyTorch in open source, and then do a similar approach as NVIDIA Nickel library does. So TLDR, I think we are giving the same user-facing API, And we see there is a need to support both transparent paths, which we have, and also the explicit paths, which both we and NVIDIA library has. We are actually working with NVIDIA to consolidate this support and make it available for the open source community. And we are going to open source our internal code stack very soon, later this year.
Yep. Yeah, that's exciting. So I think this last question is, I think we're running out of time. So probably the last question, it's probably more general. So if you can each probably give your take on it. So can you share your insights into different challenges as you scale even further? Like go to larger distances or go to different workloads like post-training? Do you see further optimizations beyond what you already shared? Or the current optimizations are like, enough to be applicable generally? Ashmitha, why don't you start?
Yeah, I think from the networking side, I think the challenges would still be the same, just that with larger distances, it'll probably aggravate more. So, with longer distances, definitely the probability of packet loss is going to be higher. So we have to think of having some kind of effective retransmission mechanisms that can, like the selective retransmission, which can actually just retransmit the lost packets instead of Rocky V2, which has like a go backend mechanism where all last 10 packets from the last ACK packet has to be retransmitted. So that can kill our throughput and also our flow completion times. So having this kind of selective retransmissions and also with respect to transports, like with larger distances, having lossless transports is going to be harder. So we might have to think about having like different kind of maybe lossy transports like TCP or for very large distances. And congestion is also going to be an issue with larger distances. So our transport has to be like effective enough to have this kind of congestion control inbuilt in it. So and also maybe as we scale our clusters, which as they get bigger, so the cross-region bandwidths are also going to get affected. Like they might probably reduce. So there are a lot of implications, but
makes sense. Exciting times.
Yeah.
Min, why don't you go ahead?
Yeah. So in addition to this transport level innovation we are continue doing, I would say we are also seeing a lot of new requests coming, as Adi mentioned, for post-training, for inference. And one specific example is for post-training, we need to enable asynchronous communication, which we cannot achieve with classical collective nor P2P. So we are considering RPC and one-sided communication for this communication scheme. The other example is for inference. It's a very low latency and fine-grained computer communication domain we need to take care over there. So having some NV-Schman-like device-initiated communication support would be something emerging at this moment. So it's keeping coming. We know some of them. We are working on that, but we cannot predict all of them. So we are keeping improve.
Makes sense. That makes sense. Yeah, we're only 1% done, right? So Saif, why don't you go ahead answer this?
Yeah, so with respect to, I think, scaling, as we go large distances, the number of GPUs will be in order of 100,000s of them. So there would be a monolithic job model would hit limitation at some point in time because you'll halt everything for training. So that's one. The other key aspect is very likely the way data center gets rolled in and set up is that they'll be of two different generation GPUs, right? Because you can't have just one generation of GPUs landed at the same time across two. So what this gives us means is that a similar problem where you waste your GPU efficiency because one GPU is slightly faster, able to compute the same amount of batch within X duration, but this is X plus Y, and you have you make the other weight Y duration every step. So you need to figure out further mechanisms of doing an optimization all across the stack in order to leverage your GPU very effectively so that there are no bubbles and handle the collectives that span across two different GPU versions with potentially differing NIC capabilities and over longer distances, which is likely to be often order of like, higher oversubscription ratio. So that means you have much less bandwidth too, not just latency. So in that way, you have to design your parallelism that goes across like longer distances to be bandwidth aware in some sense.
Awesome. Right on the time, to the second. So I think I want to thank our speakers as well as the audience for engaging in this panel by submitting questions. And we want to thank you for your time. So this concludes the programming in this room. So we can go back to the main ballroom, I think, to continue with the rest of the talks. Thank you so much for your time. Appreciate it.